Physicists, air traffic controllers, and video game creators all have at least one thing in common: vectors. What exactly are they, and why do they matter? To answer, we first need to understand scalars. A scalar is a quantity with magnitude. It tells us how much of something there is. The distance between you and a bench, and the volume and temperature of the beverage in your cup are all described by scalars. Vector quantities also have a magnitude, plus an extra piece of information: direction. To navigate to your bench, you need to know how far away it is and in what direction, not just the distance, but the displacement.
The magnitude will be a number, so a vector can have a magnitude of 5. This is the part that tells us how much. But it also has a direction, meaning 5 of something in a particular direction. This is why we represent a vector with an arrow. The length of the vector tells us the magnitude, so a longer vector means a greater magnitude, and the direction the arrow points, relative to some axes, tells us the direction of the vector. Many vectors are simply displacement vectors, denoting how far an object has traveled and in which direction. If such a vector connects 2 points, like A and B, we can call this vector AB with a little arrow over it. That's one way to represent a vector. We can also just refer to a vector with a letter, like U. Different vectors with the same magnitude and direction are called equivalent vectors. We can also perform multiplication with vectors. The simplest way to do this is called scalar multiplication. This is when a vector is multiplied by a scalar, which is just a number. So if we have some vector u and we multiply it by the scalar 2, all we do is double the length of the vector, making it start from the same point but reach twice as far in the direction it is pointing. So when multiplying a vector by a scalar that is greater than 0, we just multiply the length of the vector by the scalar. If the scalar is less than 0, or a negative number, we still alter the length of the vector in the same way, but we also reorient it to point in the negative direction relative to its original position, which is just precisely the opposite direction, or 180 degrees away. So vector u times the scalar -1 will just flip it over in this manner to give us -u.
Let's say you and a friend are moving your tent. You stand on opposite sides, so you're facing in opposite directions. Your friend moves 2 steps to the right and 3 steps forward, while you move 2 steps to the left and 3 steps back. But even though it seems like you're moving differently, you both end up moving the same distance in the same direction, following the same vector. No matter which way you face or what coordinate system you place over the campground, the vector doesn't change. Let's use the familiar Cartesian coordinate system with its x and y axes. We call these 2 directions our coordinate basis because they're used to describe everything we graph. Let's say the tent starts at the origin and ends up over here at point B. The straight arrow connecting the 2 points is the vector from the origin to B. When your friend thinks about where he has to move, it can be written mathematically as 2x plus 3y, or like this, which is called an array. Since you're facing the other way, your coordinate basis points in opposite directions, which we can call x prime and y prime. And your movement can be written like this, or with this array. If we look at the 2 arrays, they're clearly not the same. But an array alone doesn't completely describe a vector. Each needs a basis to give it context, and when we properly assign them, we see that they are in fact describing the same vector. You can think of elements in the array as individual letters. Just as a sequence of letters only becomes a word in the context of a particular language, an array acquires meaning as a vector when assigned a coordinate basis. And just as different words in 2 languages can convey the same idea, different representations from 2 bases can describe the same vector. The vector is the essence of what's being communicated, regardless of the language used to describe it.
We can also use this information to do more algebra with vectors. If we have a vector A with components A1 and A2, and another vector B with components B1 and B2, the sum of these vectors, or A plus B, will have the components A1 plus B1 and A2 plus B2. The same can be said for vector subtraction. We just subtract the corresponding components. In fact, let's quickly mention some important properties of vectors. The commutative and associative properties of addition apply to vectors, like the way that A plus B equals B plus A, and the way that A plus the quantity B plus C equals the quantity A plus B plus C. Any vector plus the zero vector, which is the vector with zeros for all its components, will simply give the same vector we started with. Any vector plus the negative version of that same vector, which is simply a vector minus itself, is the zero vector. While we can't add a vector and a scalar can be distributed across a sum of vectors, and a vector can be distributed across a sum of scalars. A product of scalars times a vector is the same as one of the scalars times the product of the other scalar and the vector. And 1 times any vector is simply that vector. Those are the important properties we should understand. The reason this is useful is that algebraic manipulations can become much more intuitive, as operations like multiplying a vector by a scalar are reduced to simply distributing a number across a binomial or trinomial, which is trivial algebra. We can also add two vectors together without having to draw them. We can simply define one vector, A, which we can say is equal to 2i minus j plus 4k, and another vector, B, which is I plus 6j minus 2k. Then to do something like 2a plus 3b, we can simply change A and B to this other notation. First, we distribute each scalar across the sum it operates on. Then we simply combine like terms and we end up with 7i plus 16j plus 2k. And we have performed this complex operation using simple algebra. Now that we know how to perform a few different operations with vectors, let's check comprehension.